My name is Bob Willis, and I'll be talking about two subjects during this hour session. And I hope to have a guest to support me for the robotic soldering side, and also a guest to support me on the low temperature side. Now, just a little bit, why am I here? So basically, I am here to plug my book, but it's free. So I don't see that as a sales pitch. But the other thing is, I've been playing football, and I still play football, twice a week, and I scuba dive. And unfortunately, a couple of my friends have actually passed away because of cancer. And that's the reason that I'm doing this presentation, to support a charity to raise money for cancer research. So with this presentation, you get a free copy of my new book, which is available online. It's free, but also you also can have a copy of all of my textbooks free to download and pass on to your colleagues. There's a QR code. All I ask is if you'd be kind enough to give a small donation, that would be fabulous. So basically, the book is available as a Flipbook, so you can look at it online. But it also is a PDF you can download. You've also got all of my back catalogue of soldering books, which you can download and again share with your colleagues. There's no point in having sort of knowledge on my computer when I'm retired. So that's the reasoning behind it. So that's the advert out the way. So I very first started my career looking at robotic soldering in 2003. And that's not when I started, obviously, but it was in 2003, and I was invited to solve a robotic soldering problem. And what you're looking at here is poor solderability. It's got nothing to do with robots. It's got nothing to do with the solder. It's all about the base material in this particular case. So we've got an open solder joint there. So I told them that and then went home. But I was always interested in robotic soldering from that point in time. I was invited with a friend of mine at NPL, National Physics Laboratory, to get involved in a little project on high temperature soldering. And this is looking at soldering with lead-based alloys, so high temperature for the oil and gas industry, but also looking at tin, silver alloys, so a variety of materials. And we produced two reports, which are again free of charge if you're interested, looking at the technology, and that was back in 2014. Just a little insight to what's happening in sort of the world of robotic soldering. I always do surveys when I'm doing webinars, and this just sort of gives you an idea. So in 2015, there was only a small number of companies out of 100 guests on my webinar actually using robotic soldering. But as you can see, as we move to 2020, just during and just before the pandemic, that there was an increase. So there's a lot of interest in the use of robotics in a soldering capacity. Now, what are the benefits? Well, my obvious thought was the benefits, really, it's all about the economics. But if you look at this graph, they were saying that 62% of the people on my webinar said that, no, it's quality improvements, it's consistency, and also trying to overcome the problems of labor shortages, and of course, the cost of training. What sort of alloy were you interested in using? Well, the majority of people are interested in using SAC alloy, so lead-free materials. But I obviously started off with an interest in high temperature, and more recently, I've done trials with low temperature. But it's a little bit more demanding because there only seems to be one supplier out there of cord wire for low temperature, and it's probably all about the demand for the material. But the low temperature material does work quite nicely. And again, of the people I asked them what sort of standard they tended to work to. Well, as you might expect, the majority of customers in our industry are really working to level 2 and level 3 of IPC. And in my opinion, my humble opinion, to meet level 3 with robotics is easy. It's not difficult. I mean, in any manufacturing environment to meet level 3, minimum 75% fill of the plated through hole. So with wave, selective, or any of those processes, it's not difficult. So what are some of the benefits? Well, reduced cost of wave and selective soldering. The processes are big machines. They're using a lot of energy. And of course, their footprint size on the shop floor is quite colossal. So again, there is an advantage there. Using work cells, I mean, it's great for an engineer to buy a robot, and he then programs it and does a little bit of work and then gives it to the production department and the operator, and then he goes and plays with other toys, new toys. But what I would say is try and bring the production staff along with you, train them how to use the machine, then start to integrate more machines. So a person is perhaps not doing manual soldering anymore, they're going on to automated soldering, but they're doing and running 3 or 4 machines as opposed to 1. There is, and there always has been, a lack of skilled training, but that's now been addressed by the IPC over many years and all the IPC trainers. But you know, increasing the skills of production staff, I think, is very, very important. And that's how I started training people in the very first place. So just to give you an idea, there's 2 types of robotic soldering. One where we're using something that looks like an operator. We have a soldering iron, we have solder, and basically we're taking and reproducing those techniques with the process. And they're available from a number of suppliers out there in the industry. More exciting to me, possibly, is laser soldering, because I think it's much faster. But like any automated process, you have to understand it, you have to introduce the materials correctly into manufacture. So this just shows that there is no contact with laser directly onto the PCB. We're just feeding the solder to make that interconnection. And if you look at this example, this is just an example of the soldering process. And you can see the solder is being fed to the joint in a controlled way, and we're making contact with the pins. You'll also notice, those people that have got good eyesight can notice all those little solder balls on the surface. And one of the issues about any automated process like this, where we're trying to go faster, because production managers want you to go faster when they get a process going, is we can get solder balls. Some of those solder balls, we know where they come from, and we'll talk about that a little bit later on. This is just an example of laser soldering. This is on one of my old customers' boards when they were implementing the technology, and you can see the cord wire being added, but you might be able to see that the wire seems to be indented. So basically, during the feeding operation, we're actually indenting the wire. And that's very common practice throughout the industry to reduce the possibility of solder balls being produced during the soldering operation. It's not to say there's a problem or one wire is better than another, but if you use the technique, it eliminates that variability, and then you select the best wire for the job as well. So if I just take an example here, I just showed 2 cord wires, and what I've done, I hope to make it clearer for you, is that where the wire has been indented, we're actually puncturing into where the flux is, so the core of the flux. So the X-ray is a nice way of illustrating this. And if you wanted a quality control check of how good your indenting process is working, then just use your X-ray machine and see that you're indenting into the wire. And where this becomes a benefit is that just before we actually go into a liquid phase, it actually becomes a liquid, and the force generated, or the outgassing generated by the flux during the soldering operation would generate those solder balls on the surface of the board. This is how this is overcome. So this video clip just shows you the flux coming out of the wire onto the surface. Now, it's not going to reflow because I've mounted it on a hot plate to illustrate this to you. And that's I do this trick video photography all the time because it explains a point, you can see what's actually going. So that's one of the benefits that most suppliers have available as a standard feeding process. If you want to look at process control or quality control of the process, one of the nice things that we can use is non-contact measurement. And I was working for a automotive company, and I just basically went to the maintenance department and borrowed their IR sensor. And you'll find quite often in your own company, you might find in the maintenance department they have one, and it's just a great tool to be able to look at the soldering. But also, one of the things you can do is measure the temperature on the board when you're introducing possibly nitrogen around that soldering area, when you're using contact soldering. And you can look at the flow rate of the nitrogen around that particular area. And you can adjust the temperature by looking at flow rate as well. So it can be a preheating exercise as well. So there's lots of little nuances that can improve the process. This is all included in the book, by the way. I just thought I'd mention that. Now, one of the other things that I was involved with, and a good friend of mine that I've known for many, many years, Claire from WNIE, is in the audience, and we created the robotic soldering experience. And we were going to run this as sort of training workshops and things with materials and robots. Unfortunately, we didn't plan for COVID. So COVID 1, robotic experience nil. You can see I'm getting back to that footballing analogy again. But all the videos that we made on defects associated with robotic soldering, they're all online. You can still watch them. Hopefully they're a useful educational tool for you. So again, that's something that's available. Just to go in a little bit more close up, I thought I'd show you a example of robotic soldering, but with low temperature alloy. So we're talking about tin bismuth or tin bismuth silver, and this is a slow motion. That was a slow motion view of the soldering operation, not what you'd normally see in a production environment, but just gives you an idea of what's actually happening within the process. So just to show you a few examples of low temperature solder with robotic soldering, I've illustrated some here. So what you're looking at on the top images are perfectly good solder joints. You will notice a couple of little things, and I'd like to just pick that out for you. First of all, if you look at the pictures, what you can see those little lines here? That tells me it's a contact system, and it's an old school contact system. So basically, you're coming down to the surface of the board during the soldering operation, and if you're then going across the surface of the solder resist, it's just a little scratch. That's all it is, just a little scratch in the surface of the solder mask. It is no real issue, but I highlight it to you because there's bound to be some quality engineer, which I used to be, highlight it to you. Another example here on the top left, right, as you look at it, is some pads that the solder hasn't covered all the pad. Doesn't matter. You don't have to fill the whole pad. It's just the design of this board was produced to allow contact soldering on an older style, perhaps a lower generation machine, where you're coming down to the surface, contacting the surface, and the bigger area you can make contact with to do the soldering operation, there's a benefit. So sometimes you design things to improve processes. On the images on the bottom, what I've done is I've taken the connector off the top. Because one of the things with through-hole soldering, and this is true of selective wave soldering, everybody wants to know how good the solder fill is, how it's filled the plated through-hole. So if you're looking at on the robotic side, you may have to mechanically remove some of the parts just to get a feel for the quality of the soldering. But I've done that for you in these two examples, and you can see that, yes, the solder hasn't risen up and wetted out across the whole of the pad. It doesn't matter. It's still a perfectly good solder joint. However, you've got in excess of 75% fill. If you have, which a lot of companies have today, X-ray capability, this is just a nice example where you can see the quality of the soldering. So this is, I would say, in excess of IPC level 3. It hasn't wetted out over the surface of the pad. And this is something I wanted to highlight, that when you're looking at robotic soldering or any process, look at everything. And I know in SMT, we talk about surface finish and solderability, the quality and consistency for our SMT process. It's going to be exactly the same if you look at robotic soldering. Because remember, you've probably taken that board and passed it through 1 reflow operation, 2 reflow operations. You may have even had a pre-bake prior to those reflow operations. So the poor selective robotic soldering system and the solder has to overcome the solderability variation on those PCBs. So please just don't think you buy a new process and you can just carry on the same. Solderability or wettability can be perfectly good with any process, but you just got to think about finishes. I know that, for instance, tin is a very popular finish in the industry, very popular particularly with the automotive. It is one of the, well, in my opinion, one of the worst finishes, but personal opinion. Give me gold, give me OSP that's made by a good vendor. I personally have those any day. But anyway, personal opinion. So just a strange coincidence, if I may, is that I said there's only a couple of suppliers of cord wire with low temperature. One of the strange things we did find is that although we had no problems with feeding the material, soldering with the material, making great joints with the material, some of you will be aware that with low temperature materials, the material itself can be quite brittle. And that's one of the things you've got to consider when you're using it on your product. Will your product be suitable for the use of low temperature? Well, one of the nice things is those guys who are suppliers that you will be talking to today, and we'll be hearing from one a little bit later on as well, have developed the next level of low temperature materials. Materials, you know, the plus, because they've improved the material reliability. They've had to look at temperatures which are slightly above, but still below what we're used to with SAC alloy. So you've got that nice sort of balancing point, and they can be readily available from a number of suppliers. But just to let you into a little secret, that the problem I did have with some cord wire, with 2 tests we were running, is we had the wire break. Literally what happened, not on the machine at all. Machine worked fine. It's the operator, me. I dropped a reel of the wire on the floor, and I wondered why it had started to break up on the floor. Strange. But it was a material that had been made 12 months ago, and what had happened is the structure of the material structure had changed slightly. We're still not 100% clear why, but it's something that we're looking at. I mean, it's a minor thing, honestly, but it was just such a surprise to me. And what I'm just showing you here on these examples, you can see the initial cracking in the wire. This is before use, obviously. On these 2 other examples here, I've highlighted it after indexing. You remember I said that we index wire, we put little holes in it to allow the flux to come out, and you can see the little cracks there. Again, it's irrelevant probably for the process, but I always say if you're an engineer, you want to know everything about your process. Whether it's going to affect it or not, try and understand the process in as much detail as you possibly can. So just a couple of examples, again, like I was saying about low temperature, and I'm just showing you the soldering operation take place on these couple of videos. And so that's one, and then a close-up of second 2 joints. So this just sort of gives you a feel of the process. Now, that is slow, but I've slowed it down so you can watch it. It is a lot faster, and of course, your production manager, when he buys you a brand new machine, is going to want it to go as fast as possible, but you just got to find that sweet spot. to get the product you want, the quality you want, with the materials you're using, and meet the standards. So just again, an example of these joints. You can see, again, I've done some x-rays. My good friend Keith Bryant, who's over there in the corner, organized these ones for me. And also some microsections just to give you a feel. So these are examples of joints with tin bismuth silver material. And you will notice there is a few here where we haven't got 100% fill. And probably I would suggest that the ones on the left-hand side that you're looking at is probably below IPC level 3, but would meet IPC level 2. Okay, but that's something you evaluate. So when you're looking at a board for this process, all the things you know about, all the things you've learned about thermal demand are also important with contact soldering. So again, in my book, I talk about the thermal balance, all the things you probably already know, but it's just true of this process as well. And the neat thing about individual soldering, contact soldering, is you could go along and solder 3 joints, and because that next one has got a very high thermal demand, jump over, do 2, and the energy is going into the board, jump back, do that one. So you're just using the process to overcome if you've got a poor design. So just a simple, nice example of that. This is just a reminder, if you want to download the book, you've got the code there, and again, it's online, it's free, you can download it. If you want to make a small donation, that's absolutely fabulous as well. So, we're just at 22 minutes past, so everything is going well, I hope. I was just looking in the audience for the colleague that was coming to talk about or answer questions on robotic soldering with me. I don't see him in the audience, so no problem. No problem. What I'm going to do, if I may, is just pick up if there is any questions on this particular part of the presentation. Do we have a radio mic, or we can use this one? Yep. Oh, my beautiful assistant will rush to you, and she only gets up because she knows she's going to get at least 2 people ask a question. And the question mustn't be, when are you going to leave? When are you going to pack up? So, a couple of questions before we move on. Come on. The book's free, so that's one question answered. Sir.
Yeah, hello. When do you choose between the laser versus the contact?
Okay, it's a good question. I've used both processes, and I was working for an automotive manufacturer, and he got this brand new line. He just, it's at the back. You're not allowed to look at it, but it's there. And I said, well, you've been using contact soldering for quite a long time on these sensors that he was producing. Why have you bought another line? He says, well, everything's working well. And I said, so I got out a video of the one I showed you of one of my other customers, and he was just, whoa. The speed. So I think the speed is one thing which is very beneficial. I think that flexibility possibly on temperature might be a nice thing. And if you look at the systems in the show, I was looking at one, I dragged a salesman to the stand at 8 o'clock. That's unheard of. But he went through the whole thing with me. And I was impressed by this, a supplier, on the improvements from his original laser system to his new one. The versatility, the quality control, the data collection. So if you're into medical or aerospace and you need that traceability, automotive need traceability, capturing the information per interconnection, per joint was very impressive. It's going to be more expensive. So it's that balance. But it's certainly, from a speed perspective, I think that's something very worthwhile considering and talking to the boss or yourself if you own the company. Okay, another question, sir?
Yes. Can you refer also for pins and beads that are welded on aluminum blocks?
I think in all reality, you'd have to look at some sort of preheat. You know, if you were using contact soldering or laser soldering, it may be possible, but if you've got a chunky bit of metal there, you've got to think about preheat. And that can be, you know, quite simple, radiated preheat. Certainly the laser systems give the ability nowadays to look at larger areas. So you introduce preheat based on the laser and then focus in to the individual joints. That's possible, but without knowing the size, the perspective of it, it's difficult for me to comment, but possibly that might be an option for you. Okay, thank you very much for those two questions. I really appreciate it, and thank you for my beautiful assistant, and she will be... Hey, hold on a minute. I don't mind you giving a nice round of applause and a clap, but, you know, save some for me as well. Hopefully. Not yet, later. Okay, so on to low temperature side of things. Just on to low temperature side of things. This is something that sort of interested me over a number of years. And I have to say, the guy who gave me an interest in it is Ning Chang Lee of a well-known solder company. And I was always fascinated by the work that he'd done. But if you're interested in finding out more about low temperature solders, there is information in all of these books, but really the sort of most up-to-date is the last one I show here by Jaspin Barr. And that's basically all the work that's been done on a research project in the US. So that's the sort of most up-to-date. And of course, if you go to SMTA exhibition or some of the other exhibitions, a lot of their technical papers cover these particular subjects. So that's the best book. I'm not here to sell books, by the way, but that's the best book. In terms of other material, again, I've got something that, if you're interested, it's free of charge to download from the SMTA website. And this is my inspection criteria and also hand soldering and desoldering with low temperature alloys. So it's a set of charts. You can print them out, put them on the wall, use them as training. So they exist. Again, they're free. So why are we interested in low temperature and low temperature processing? Well, basically, everything is getting smaller, as we all know, and components are getting thinner, as we know, and most of them now have 1, 2, or maybe even 3 silicon dies mounted to the surface of that substrate. So it makes it A, higher mass, B, sometimes those dies are off-center. You know, it's not one on top of the other on top of the other. Sometimes they're slightly offset. So there is a thermal change in components during reflow. So if we consider the PCB can move, we know the component can move during the soldering operation. So we've got to try and minimize that possibility of that actually happening. And that movement of the component or the PCB during the soldering operation that we do every day, whether it be vapor phase or convection reflow, have led partly to some of the other defects that we see in manufacture. So head in pillow. If the thing isn't in contact with the solder for whatever reason, then you're going to get an open joint, unless you've got a lot of solder to bridge that gap. But that solder oxidizes during the soldering process, and if the things are not sitting together, you get an open. Non-wet, where the solder paste can actually lift up on the ball itself because there is a gap there. So again, another potential. If the component stays on the surface of the printed circuit board and the paste is there and the heat is there, we should make joints. But that movement of components, and I personally believe the semiconductor industry should be doing all our work for us. They should be doing measurements, shadow moire measurements of components, and actually giving us a kind of recipe on how to make sure their components work successfully in reflow. But what's happening is basically production engineers and scientists have to do all this work in contract manufacturing, where I personally think it should be the supplier. Personal opinion. Hopefully there's no semiconductor guys here to have a go at me, but I've got a thick skin, so it's not a problem. So component warpage also has given us problems where we've used stacked components. This is just an example of one of my test boards, and you can see here where we've got opens on these POP devices, package-on-package technology. So the part moves, so we've not only got one row of joints, we've got another row of joints, and then another row of joints to make an interconnection too. And if the packages warp, you get opens, and this is just a nice example of you've got part of the solder was in a liquid state, it's deformed slightly, but there's no flux there to make that joint, so consequently we've got an open. And we've got a nice piece of trick video, Bob's trick video, again, just to illustrate this point. So if you've got a package or a board is warping, and the solder can be in a liquid state, the ball can be in a liquid state, but if you can't get the things to join together, you get a nice open connection. And this is what people are now doing more and more in contract manufacturers, trying to understand the components and also how they perform in the reflow soldering process. This is Shadow Moire, and this just illustrates a technique to look at this change in shape of parts during the reflow operation. Now, again, low temperature materials are not new. They've been around for a long time. In 2001, I had the pleasure of taking a whole group of engineers on a holiday, and it was all paid by our government. It was wonderful. We all trooped off to Japan, and we went round all of the different big companies, manufacturing companies, and they illustrated all of their stuff. They showed us what they were doing, talking about bismuth alloys, zinc alloys, etc. But there wasn't a lot of interest necessarily in low temperature in sort of the early introduction of lead-free, because a lot of work had been done, but not the degree of work that has now been done to develop new materials. Because people had early life failures on test boards, so I guess the low temperature materials were put to one side. SAC was more interesting. SAC was affordable. I question that, but anyway. But it worked and gave pretty good results. But the low temperature soldering didn't perform as well. But what about all the guys that could have used these materials 10 or so years ago? Anyway, another conversation perhaps. But low temperature materials have been introduced. They are in products today. And this is just an example of a very thin printed circuit board which is being handled delicately by somebody on a laptop. And inside that product, that particular product was exclusively made with low temperature. Just an example. So INEMI, when they've been doing their project work over the last few years, they identified a roadmap. Now, whether we're sticking to this and hopefully Chris from Indian will sort of bring us up to date, whether this is a reality or not a reality. But you can see there is a lot of interest and there's the potential for growth in low temperature materials. And in my experience with hand soldering, desoldering, reflow technology, wave, selective, and all that sort of nice things, if we're talking about standard SMT, standard through-hole components, it's not that difficult. It's fairly easy, and I think you can have a good, reliable product. But when we start to talk about area array packages, and we've talked about larger packages, then perhaps we need to understand what's going on. So this video clip, I'm just illustrating us soldering with low temperature materials SAC balls. And what I will illustrate in a moment with a pointed stick, that the solder has reflowed, the ball has not reflowed. You can see the pointed stick. Yeah, sorry about the bit of crud on the stick, but you're doing these experiments, you can't necessarily see everything. But what I'm illustrating simply is the solder's in liquid state, we soldered to the packet, the ball, but the ball has not become liquid. But with a lot of research, companies have identified that wear and the volume of solder paste that we're actually using for this particular process with area array packages is quite critical to get the reliability we actually want. So when you're talking to a supplier, you're going to possibly have to change some of the things you do, but this is changing stencil apertures and things. It's not something that we're not familiar with, but it's a process that needs to be understood. Just like lead-free all those years ago, it's a change. One of the other options available, I kind of not really, very keen on this, but for completeness I mention it. It's reinforcing materials. There are 2 or 3 suppliers out there that offer solder paste with glue in. I mean, in simple terms. So we've got an epoxy resin within the system. And if you look at the material from a paste point of view, you look at the paste and you print it, it reacts in exactly the same way as solder paste, because it is solder paste. But what it's actually doing is creating a fillet around very small joints and giving some more robustness to overcome any of the issues with the low temperature material. And if you just look at this view here, this is just a couple of, again, Bob Willis's trick video. And you're just looking at the printing process and the release of the stencil from a sheet of glass. And it's just a nice way of understanding what's going on in a process. And a lot of engineers have done this work in the past and actually looked at the volume and release and amount of fluid that squeezes out on the stencil, etc. So I just wanted to illustrate that. But that's an example of me using joint support paste material. So it was a little bit more challenging for me than traditional material. Now, for those of companies, engineers out there that are using intrusive reflow, how many people use intrusive reflow, pin and paste reflow out here? 1. So you haven't read my other book? So the other book on intrusive reflow is completely free again, and it goes through how to introduce it, design rules, process, etc. And it is a doddle. It's not difficult, not complicated. But all I'm illustrating here, and this again example, is low temperature material. We're reflowing with pin and paste, and all we're doing is getting the volume of paste right for the plated through hole and that interconnection. And if we've got those 2 things right, then we're going to get perfectly good joints, certainly exceed level 3, which I've hopefully illustrated in those examples. Now, previously, I mentioned a good friend of mine who's now retired, Ning Chang Lee, and a couple of years back, I did some experiments with indium alloy. And indium alloy, or indium alloy paste, which Chris may allude to, is a material which has been available for many, many years. And I was running a rework event, actually in Germany, and what we wanted to do is demonstrate it as part of the process. So basically, I've localized printed solder paste onto a board as part of a rework process. And what you're looking at here is just a video clip just illustrating low temperature material being used in a rework environment. So we're using a BGA rework system. We've got paste, you can see it reflow, we've made some joints, but all of those balls are solid. So you're soldering to the balls, they're not becoming part of the full structure, we're soldering to them. Just like you would do with high temperature balls using a normal soldering process. And just to illustrate, there's some x-rays. And some of you with good eyesight, I've highlighted it for you. If you haven't got good eyesight, there are some voids. But remember, the voids you're seeing are at the interface, because that's the only bit that's become liquid. And what we then went on to do is just change the process, change the profile a little bit for our rework, and significantly improved the results. But I like to show the good and the not so good, perhaps, although I'm not necessarily an advocate of zero voids. I think that the strive to reduce voiding in some situations is unnecessary, in my opinion. But if you need it for your particular customer, then no problem at all. Or I'll speak to him for you if you want to. Okay, so that's just an example of some close-ups and voids. There's some pretty pictures, some x-rays again. You can see the voids, just the interface. Here, I've just ripped the components off the board, as you do, doing your die and pry test. Perfectly good joints. There's nothing wrong with the joints and the interconnections. So that's just an example. Now, indium indium paste for rework using these materials is expensive. So when we're talking about these type of low temperature materials, but you have got a tube of paste that if you look after it will last a long time. So don't look at cost, look at is this material or an alternative supplier of this material going to do what you want to do. And in a rework situation, using solder paste is probably better than using just gel or flux, in my opinion, because you're adding solder volume. So if there is any variation in height between the board flexing, the component flexing, you've got something to bridge the gap. With a gel or a liquid flux, it won't bridge the gap. Solder makes a connection, which is what we're interested in. Just moving on a little bit, on the wave solder side, I've used bismuth materials for wave soldering of some relatively simple printed circuit boards. It's just some examples back in 2004. This is some examples of selective soldering. Again, there's suppliers of materials out there, and you can look at the top row, perfectly good joints, you know, not really an issue. There's some things, tweaks you have to do to your machine to implement low temperature alloys, and it's all around probably set points of temperature, set points of temperature, of cutout temperature on the machine. And if you're using low temperature materials for rework and repair, you've got to get the manual out. You know that on a manual for a soldering iron, desoldering station, you have set points, cut-off times. They're quite annoying when you're using low temperatures. So you've got to get the manual out, read it, and drop those temperatures down. And if you've thrown the manual away, like I've done, you have to go online and get another one. But that was the most annoying thing about doing some of these exercises. What I've shown you here is some joints that you can see some cracking on, but this is where I've been doing pull tests. So when I've done pull tests, normally speaking, and obviously it depends on the size of the pin, obviously, and the material, but generally speaking, it's always the pin that breaks, and that sort of gives you an idea. One of the other things I think you've got to think about is fluxes and compatibility. So if you are thinking of going to low temperature and wave and selective, look at the fluxes. You know that we do a lot of work on SIR testing to approve no-clean materials. Well, think about it logically. You've been told for many years that if you're going to be doing wave soldering or selective soldering, you've got to get those temperatures right to deactivate the flux so we're not going to get any issues, which is absolutely right. So we're going to be running at low temperature alloys. So does that mean? Well, yes, it does. You should look at your flux and flux material compatibility. And SIR testing, which is what I've historically used, and my good friends at MPL, National Physics Laboratory in London, spent a lot of time doing SIR testing for customers to approve materials and fluxes. And this is just a pretty picture of one of my test boards going through a selective soldering process. So it's already been fluxed, and you guys all know, nozzle's just going to troop along and do the results. But what we want to see is what impact that might have. SIR testing is using generally standard test boards, and we're putting applied voltage and we're exposing it to temperature and humidity to a set standard, and we're looking at changes in resistance value. So what you're looking at in that example is the squiggly lines. You can see I'm technical. The squiggly lines illustrate changes in resistance. And you can see here the limit is 8. So everything is above that, which is good. That's really good. But here's a few examples taken from Jasbar's book. And this is tests that have actually been done on different materials. And they did notice that where they perhaps haven't looked closely enough at some of the liquid fluxes they were using for some of their trials, then they did see some differences, not failures necessarily, but differences in surface resistance. So it's something that you really need to think about and consider. Just a couple of more examples before I get my guest up here on the stage. I have done temperature cycling on lots of different boards. Now, Bob is self-employed, or was until I retired, so I don't have a budget for most things I do. So the practical stuff I do I cadge, I take advantage of other people's hospitality sometimes. So a lot of the testing I did over the last few years on the low temperature side has always been to standard temperature cycling regimes. So that's -40 plus 125, which is not appropriate really for low temperature because you're testing it way above what it was actually designed to do. So just bear that in mind. So any of you that know the business and look at this and think, what the hell is he testing? It's because other people are doing testing and I can put my boards in a chamber and get some information, some results. So just bear that in mind, please, for a moment. So basically, I've taken a lot of through-hole components, a lot of surface mount components, and done all that nice stuff and the nice, pretty microsections afterwards. And you can see, yes, with those temperature changes, you do see some cracking of joints, but nothing that would cause a failure on that particular product. You'd have to go way further to ever get a problem. We did notice on a few examples pad lifting and fillet lifting, but that's something that many of you probably have in all of your products if you're running lead-free anyway, if you look close enough. And this is simply the board is expanding and contracting during the soldering process, and as it solidifies, the solder solidifies, the board comes back and it sometimes lifts and separates the pad. But this is an old thing. It's been around since the year dot. There may be a factor in that the alloy, being harder, might have contributed to it, but it's something that we've seen many, many times. If you've got a sexy X-ray machine, which really sort of gets really high definition and beautiful pictures, you can just about see some cracking at the top here, and there is some little cracks in here, which I showed you with a microsection. But again, nothing that would cause a failure. One of the things to look carefully at is QFN, LGA components. Because these components, you probably know, we solder, and we pretty rarely actually get side fillets because they're not designed to be soldered. When they're cut out, because they're like chocolate bricks, you take Cadbury's chocolates, you break a strip, or 2 strips if you're naughty. So basically, you can't get plating to those areas. So manufacturers now do secondary plating, or they have dimples on these surfaces, which they plate, which allows them to get pretty fillets, like I show you here. And I think that is a benefit, certainly if you were looking at low temperature, to try and look at if you can improve the fillet formation to give mechanical rigidity. And this is not to do with temperature cycling, this is to do with dropping the board, flexing the board, etc. So these are just some examples after microsectioning. Bear in mind the temperature is way higher for longer than I would now consider appropriate. A lot of companies are going to 0 to plus 100 or minus 10 to 110 degrees C for their thermal cycling. But those are thermal cycling failures, or pretty much failures, on QFN, LGA components. But this particular example is mechanical, and it's a flexure failure. And this was actually on a product where the company was using a low temperature alloy. And in my opinion, they shouldn't really have been using it for that particular product in that particular environment. Again, an opinion, but that's what you're here for, an opinion. You can agree or disagree, but you're here for an opinion. All right, so another plug for the book. I'll give you plenty of time to look at downloading it. So I'd like to invite Chris. Chris will introduce himself. I'm not going to get him to sit down. We're going to stand up and chill out up here. Do you want to, not that you need the height. Okay. So Chris is from Indium, and I'd just like to say to it for Indium, thank you very much. They have contributed to the fund on my book, which is all going to prostate cancer, if you didn't know. Chris, would you like to give me just a little bit of an update on your perspective of the growth of low temperature, but also on the alloys that a lot of people will be interested in for higher reliability. Chris.
Sure. So, Bob, thanks for having me. As usual, it's a pleasure to see you. My name is Chris Nash. I'm a senior product manager for Indium Corporation's PCB assembly materials. I've been in the industry for almost 20 years. And what I'm seeing here is kind of a growth of low temp, or maybe I should say a growth of low temp interest. Because I think the implementation of low temp has been slower than we had initially expected. And I think most of that is due to the alloys that are available in the low temp space. So typically what you have is a pick your poison scenario between bismuth contained alloys and indium contained alloys. Bismuth contained alloys are brittle by nature, and indium contained alloys are, as Bob alluded to, a little more expensive. So that is your kind of the debate in your minds, whether you want reliability or do you want low cost. The bismuth-contained alloys are typically lower, much lower in cost than the SAC-type alloys out there. So it's the implementation of low temp because people want lower cost and can't handle the prices of some of the indium-contained alloys. Has been slow adoption because of the brittle nature of the alloys. We've done stuff with the bismuth alloys. The entire industry is looking for kind of what I'll call the holy grail of the industry with low temperature, being less than 180 or less than 190 degrees C reflow temperatures. And I think we're trying to do more with bismuth. But indium's kind of taken a little bit different avenue, and we're saying we can do just as much with the indium alloys or the indium-based alloys, and bringing the cost down on some of that by reducing the amount of indium present within the alloys, and maintaining the reliability, or in some cases actually improving the reliability compared to the SAC alloys out there. So I think there's going to be definite growth within the low temperature space. I think there's still a ton of interest within the industry on the topic of low temperature. And it's just a matter of what applications do you have? Can they use bismuth? Bismuth, from a thermal cycling standpoint, is not so bad. But from a drop shock or a mechanical reliability, bismuth is going to be more challenging to implement. But if you have products that are just going to, TVs, for example, are a perfect application for a bismuth alloy. You're going to get the reduced cost, you're going to get the reduced temperature, and you're not going to be concerned with drop shock, right? If you drop a TV, you're going to be more concerned with the screen fracturing rather than the solder joints inside. So if you don't have that drop shock, if it's a handheld device, you're going to want to stay clear of bismuth alloys in a lot of cases. But there's a lot of different reasons for low temperature, right? So Bob alluded to component warpage. There are applications where you have temperature-sensitive components that you can't go through some of the higher reflow temperatures, or temperature-sensitive substrates that you can't go through some of the higher SAC alloy temperatures. So a number of different reasons. There's solder extrusion that could happen as well with a underfill type application. So say you process your board with SAC-305 and you have a secondary process. You're not going to want to use the SAC-305 because you have underfill on the board, and the underfill is going to soften. If there's any voiding in that underfill, you're going to have and create solder extrusion in that secondary process by going to a higher temperature. So a number of different reasons why low temp is being implemented.
Well, thanks, Chris. I just thought, while he mentioned it, you can see I'm prepared here. We've got extrusion, but it's not extrusion as Chris was alluding to. This is just an example of one of my low temperature epoxy pastes. After reflow, we've got little balls on some of the joints. I'm thinking, what's happening here? I didn't think I've set my reflow up too badly to get a lot of balls and outgassing and stuff. But what it actually was extruding through the epoxy. So the epoxy had kind of partly cured. The material was obviously just changing it because it expands and contracts. And we've got a little balls squeezing out. Kind of neat. And when you did the microsection, you could see the material round it, and it just squeezed out a hole. Just because he mentioned extrusion, I just thought it's a perfect example. Can we go back to the other slide? The master slide. Thanks. So just one other point, because I want to stop 3 or 4 minutes beforehand, because we've got 2 other presenters coming up, and I've been to shows before where the guy on the stand just waffles on, and the poor guy's really rushing to get finished. So, Chris, just one brief other question. I know it's difficult, for engineers, but what are we looking at in terms of kind of cost differential between the high reliability low temp and SAC right now? If just an indication.
The product that you're alluding to, I believe, is the Durafuse LT material, and it will produce reliability similar to or better than SAT-305 with the right processing, depending on the processing, right? So the cost question is an important question. I think we're probably around about 20% more in cost than the SAT-305 now. So it's kind of enabling technology. Enabling technology doesn't often come with reduced cost, but it is certainly a little bit more expensive because of the indium content, right? I said, pick your poison. You still have a little bit of poison, but it's a reduced amount of poison compared to some of the higher indium content material, like what we call Indoloi 1E, which is 52% indium, 48% tin. You're going to have a much higher indium content, and the price of that is going to go up just because of the metals cost.
Okay, well, Chris, thank you very much for participating. Thank you very much for the input. I really appreciate it.
Sure.
And I'll catch up with you in a second. So that's all from me. Yep, thank you. So applause for Chris. Applause for my beautiful assistant, Claire, for handling the microphone earlier. Thank you very much for attending. I'm just going to check the numbers and just see if we've got the most people here, which is great. Just a reminder, all the stuff is there. Just flash on there. The links are there. It's free. It's free. But if you care to make a little donation, that's fabulous. Thank you very much for your time. Thank you very much for coming to Productronica. And yes, probably this is my swan song. I probably won't be back, but that's purely because of my age and my wife telling me I can't come to exhibitions anymore. Thank you very much.